All right, we will define a field in this video, and it's going to be a long definition. And when you go and you check something as a field, you're going to have to check all of these boxes that I'm about to write down. Now, having definition doesn't really mean anything if we don't know what it's trying to accomplish. And what this definition is trying to accomplish is it's trying to understand the three examples that we started with, namely the rational numbers, the real numbers, and the complex numbers. In these number systems, you can add rational numbers, you can subtract rational numbers, or add a negative rational number, rather. You can multiply rational numbers. You can divide by almost every rational number except 0. And the multiplication and addition operations they actually play nicely with respect to each other. So what is a field? I'm going to give you the morally correct definition, and then I'm going to give you the very algebraic, how do I prove something's a field definition. Okay, so the first definition is going to be a loose definition, so loosely, meaning don't ever use this. It's just what is it trying to accomplish. It's a non-empty set F with at least two elements. All this does is it rules out the trivial field, F is equal to 0, and there's various reasons why we don't want that to be a field. Let's not read too much into that just right now. But loosely, what a field is a field is an algebraic structure where the rules of arithmetic hold. Now, I'm going to add plus dividing here. So basically, a field is somewhere where you can do arithmetic, including dividing. Later on, in the next section when we introduce rings, I'm going to say a ring is a structure where you can do arithmetic, not necessarily dividing. Dividing is kind of special. But a field for right now is a structure, an algebraic structure where we can do arithmetic. That's what it is. Now, that's not the correct definition. So what is the correct algebraic definition? Well, it's kind of long. So let me say the first 4 axioms have to do with addition. So the additive checks. Sorry, let me back up for a second. At least 2 elements, I messed up here slightly, with 2 binary operations. Here we go. Plus and times, satisfying. Satisfying what? Well, the plus behaves like a plus. So we have some additive axioms, some axioms about the plus binary operation. And the additive axioms say that, well, it should be associative. I'm going to do the same order as your book, but there is not really an order here. You just have to do all of them. So associativity. So A plus B plus C is A plus B plus C for all A, B, C, and F. That's a rule of arithmetic that we'd want to hold in this abstract set. There should be commutativity. I don't need parentheses here. A plus B should be B plus A for all A, B in our field. There should exist a 0 element. Let me say it this way. The correct way is an identity, an additive identity. So there exists a 0 in our field such that A plus 0 is 0 plus A is A for all A and F. And we just subscript the 0 to indicate it's the 0 in F. You don't have to do that. 4, these are additive inverses. So given A in F, there exists B in F such that A plus B is 0. So you might ask, well, why don't you just subtract A? Well, we don't have a subtraction. We just have addition and multiplication. So how can you describe an additive inverse? Well, it's the thing you have to add to your A to get 0. Now, 0 is 0 in F, and I'm going to point out that we should also require B plus A is 0, although commutativity is actually, we have commutativity of addition, so we actually don't need that requirement. All right, so those are the additive axioms. We have a closed operation called plus that is associative, it is commutative, it has an identity, and it has inverses. So that's all 4 checks we have to do if we're checking if something is a field. And then we have some checks we have to make about the multiplication. And the multiplication axioms are similar. We have associativity of multiplication. So A times B times C is A times B times C for all A, B, C, and F. 6, it's commutative. So A times B is B times A. 7, there exists an identity, a multiplicative identity this time instead of an additive identity. So there exists a 1 element such that 1f times A is A times 1f is A for all A and F. Just like since we have commutativity, we don't actually have to list this condition, but it's good practice. And 8, inverses. That is, we need to be able to divide. So for all A and F, there exists B and F. Well, this is not true, actually. Given a non-zero element in F, there exists B and F such that A times B is B times A is 1. Now it's very important that that element is non-zero, because if you want to have a 1 over it, which is what B represents, B kind of represents 1 over it. 1 over 0 we saw in the previous video doesn't really make any sense. So we want to have a division, but we want to have a division in the only case that it makes sense. And it only makes sense when A is non-zero. All right. Great. So there's 2 more axioms. There is these are the sort of intertwining axioms. I like to think about them as an intertwining collection. So intertwining the addition and multiplication. So there's these 2 operations on our set F, and they exist sort of on their own, right? If we look at the axioms for each of them, they don't involve the other one. It's just I have 2 operations, and there should be some way of saying how compatible they are, how they work together, and this is in terms of 2 properties. This is distributivity. Your book breaks it up as 1 and 2, although it's really just 1 distributive check you have to do twice. So A times B plus C should be equal to AB plus AC for all A, B, C, and F. And then what your book is calling distributivity 2 is A plus B times this times C on the right should be the same as A times C plus B times C for all A, B, C, and F. Now, in fact, you just need one of these because of our commutativity properties. And that'll be an exercise to show you just need one of them. But nevertheless, you should think about this last collection of checks we have to do. We have to do 10 checks. It's a lot of checks. But this last collection is a compatibility check between the 2 sort of separate operations, addition and multiplication. They have to play nicely with each other. And that's what distributivity tells us.